A conservative vector field is a vector field with any of the following of these characteristics. And any of these characteristics, including the fact that the vector field is conservative, is equivalent to any of the others. Okay? One is that it's path independent. See what that means. One other is it's of the form del f for some f. It's a gradient of some scalar function f. In 3 dimensions, if we're in 3 dimensions, the cross product, the curl of the del cross f is identically equal to the 0 vector. And when I say it's equal to the 0, I really should have said identically equal to the 0, which actually I did. Okay, there's 3 of them. Okay. The integral from point A to point B of f dot ds, the line integral over any path connecting point A and point B, is the same. That's actually what we mean by path independent. And it's equal to little f at point evaluated at point B minus little f evaluated at point A. So this is like a fundamental theorem of calculus. It's like little f is an antiderivative to big F, because big F is the gradient of little f. Okay, the gradient's like the derivative. So big F is a derivative of this, so this is antiderivative of this in this sense. And we'll see how that works out too. Also, the integral of f dot ds is 0 around any closed path, any path that comes back to its starting point. Now, an example of a conservative vector field. Okay, well, I'm just going to say that this is a conservative vector field, and then we'll prove it by just taking a gradient of the function that happens to be its antiderivative, or what we call its potential function. Okay, well, g times m1, m2 over r squared times the r vector divided by its magnitude, because little r is the magnitude of the vector r, is a conservative field. Okay, it represents a gravitational field between 2 masses, m1 and m2, where r is the vector from one to the other. Actually, let's be specific, it's a gravitational force exerted on m2 by the mass m1, where r is the vector from the position of m1 to the position of m2. Now, if we assume m1 is at the origin, then our r vector is just what? I misspoke. Should be the negative of this to get the gravitational field, okay? And that's going to correspond to this, okay? So if the r vector goes from the position of m1 to the position of the second mass, then this is it. Now, that's equal, obviously, then, since the r vector is the vector xi plus yj plus zk, the vector from the origin to the point x, y, z, it's equal to this. Where I put the negative sign here, and with this interpretation, this is equal and opposite to the vector from here to there, making this a force of attraction. Now, you don't necessarily have to understand all of that, but it just so happens that my physics students are dealing with the gravitation at the same time that we're dealing with this, which is a nice conjunction. But not all of my physics students are in the multivariable calculus. So, anyhow, this is what we have. Now, and then we put it into this form. We bring the minus back out in front here. And we take this x squared plus y squared plus z squared to the 1/2 and multiply it by the x squared plus y squared plus z squared to get x squared plus y squared plus z squared to the 3/2. And now then our vector is just xi plus yj plus zk. So our force is going to be this quantity, this scalar quantity, times this vector. And then I wrote down what that is, but I've already said it. Okay, now, this field is a conservative field, and as I say, we're going to prove it. So, okay, yeah, that's all right. I thought I was missing a minus sign there, so I had to read what I said. Okay, I'm sorry. Shouldn't have to do that. Okay, so we want to find the gradient of f now. If f of x, y, z is 1 over the square root of x squared plus y squared plus z squared. Well, that's a very straightforward calculation. So I'm not going to detail the calculation. I'll just say, well, it comes out to this. And then we have the 2 here in every term. We have the 2 down here. It comes out to this. And you can work this out. Well, this is just the xi plus yj plus zk over the 3/2 power of the sum of those squares that we had over here. So if we multiply this expression by big G, little m1, little m2, we're going to get our gravitational field. So our f of x, y, z is just negative G, little m1, little m2, multiplied by the gradient of this little f function. So this is the gradient of a little f, if your little f is the G, little m1, little m2 over square root of x squared plus y squared plus z squared. Okay, and you can take the gradient of this and verify that it's equal to this. But if you've done this derivative, you've already done almost all of the work. Now, well, okay, that's an example of a conservative force field. We'll see how you can find a potential function, a function of which you take the gradient to get the vector function in a couple of examples a little bit later on.